Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome you all to MSP lecture series on advanced transmetal chemistry. This is the 7th lecture in the series. So, in my previous lecture I was discussing about reactivity and gave some introduction to coordination number. So, let me continue from where I had stopped. So, let us discuss some information about coordination number and structure. Of course, later we will be discussing these aspects in a more elaborated manner. So, molecular compounds made up of D block elements and ligands are referred to as metal complexes or coordination compounds. That means, in order to call a compound as a coordination compound, we should have a transition metal that should have bonding to ligands coming from main group elements. They can be group of atoms or a single atom or an ion which should have a pair of electrons that can be readily donated. So, we call it as ligand. So, the number of donor atoms of the ligands that bind to the central metal atom or ion depicts the coordination number. So, that means the number of ligands, monodentate ligands making bond with a metal ion or a metal atom is referred to as coordination number, which is determined by the size of the central metal, the number of d electrons or steric effects arising from the ligands. That means, when we have a certain set of ligands, whether they can offer coordination number 3, 4, 5 or 6, that depends on whether metal is capable of having that many ligands surrounding it, and also the number of d electrons and also the steric bulk of the ligands. All these factors are very important, and we have to understand all these things when we talk about coordination compounds. When we look into various coordination numbers, complexes with coordination numbers between 2 to 9 are quite well known, with not only 3D but also with 4D and 5D. Of course, in case of 3D, because of smaller size, maximum coordination number we can look for is 6, having mostly octahedral geometry, and in some cases we may have different geometries, that also we will be discussing later. However, complexes with 4 to 6 are the electronically and geometrically most stable. That means, complexes having the coordination number of 4 to 6 are the electronically and geometrically most stable complexes, and majority of the complexes would like to have either coordination number 4 or coordination number 6, and also depending upon the type of oxidation and type of ligands and type of metal we are considering. When the coordination number 4 is there, they can have tetrahedral geometry or square planar geometries. Some representative examples I can show. Let us look into 2 coordinate complexes. So, many electron rich ions, that means particularly having 10 electrons in their valence shell or D10 electronic configuration, copper 2 plus, copper is 3d9 4s2, and if one electron is promoted, it would have 3d10 4s1, and if you get rid of that electron to make monocationic, then we will be having D10 electron configuration. Similarly, in case of silver plus and gold plus, all these 3 have D10 electronic configuration, and they prefer a geometry with coordination number 2, for example AgCl2 minus, and a 0 valent complex having 2 coordination with palladium. That means, the preference is always for 4 coordination in case of nickel, palladium and platinum with D8 electronic configuration. However, with bulky ligands we should be able to stabilize palladium with 2 coordination number. In this case phosphines comes very handy, and especially bulky phosphines. In this case, tris cyclohexyl phosphine, because of its bulkiness, it has stabilized palladium with 2 coordination number and having linear geometry. So, another example is tri-tertiary phosphine. Okay. There also 2 tri-tertiary phosphine ligands stabilize palladium in linear geometry with coordination number 2. So, generally stable 2 coordinate complexes are known for the late transition metals. The 3 coordinate complexes are less common. One very important example I have shown here. In this case, because of the bulkiness of this amide, okay, hexamethyl diacylyl amide, what happens? It is stabilizing iron with coordination number 3. Here one can prepare starting from iron hydrous FeCl3 and its treatment with lithium amide of hexamethyl diacylyl. So, this is one example where, okay, 3 coordinated complex can be seen. And as I mentioned, 4 coordinate complexes are very common. So, with 4 coordination number, one can think of tetrahedral coordination or square planar complex formation, and I have given some examples here. For tetrahedral, examples are COBr4 2 minus or NiCO4 or tetrapyridyl copper plus or AuCl4 minus. In all these cases, the respective metals are in tetrahedral environment, and for square planar geometry, tetracyanonickelate and tetrachloropalladate are examples. We have plenty of examples, only a representative examples I have shown here. And also we come across, these are all, if you see, they are all homoleptic complexes. We also come across mixed ligand complexes where you can have tetrahedral as well as square planar geometries. When we talk about mixed ligand square planar complexes, we come across number of square planar complexes from cobalt and nickel group. When we look into the cobalt group with +1 oxystate, for example rhodium +1 and iridium +1, and then in case of nickel group, nickel 2 plus, palladium 2 plus, platinum 2 plus and gold 3 plus, they have a preference for square planar geometry, and we can see a large number of mixed ligand complexes. For example, if you see here, this is very similar to Wilkinson catalyst. Instead of triphenyl phosphine, we have trimethyl phosphine, and also here this is again very similar to Vasca's compound. We have trans chlorocarbonyl bis trimethyl phosphine iridium compound, and this is an example of mixed ligand complex having halide and phosphine, and then this is well known diamine dichloroplatinum compound, and of course here we also come across when we have 2 different type of complexes, 2 different type of ligands having square planar geometry like MA2B2, we also come across geometrical isomerism cis and trans. Cis and trans geometrical isomers are possible for complexes with 2 different kinds of ligands, and were first noted when Werner synthesized both cisplatin and transplatine. And of course, I shall tell you fascinating story of discovery of coordination concepts by Werner. But tetrahedral complexes do not give geometrical isomers. Werner was able to conclude that his 4 coordinate complexes were square planar. So, he did a series of experiment and also used conductivity measurements and also used stoichiometry and all those things to arrive at 4 coordinate geometry with 4 coordinated square planar geometries for certain complexes, and those very famous complexes are cis and transplatine. And of course, you are all familiar with the application of cisplatin. Cisplatin has been used for the treatment of tumors, and it is again noteworthy that only cis isomer is active but not the trans isomer. When we look into 5 coordinate complexes, we have quite a few examples. The preferred geometry for coordination number 5 is trigonal bipyramidal geometry with the D3H point group. For example, iron pentacarbonyl. In case of square pyramidal, we have this complex here having C4V point group and VO H2O 4 times. The energy difference between the 2 geometries is not large and structural transformation readily occurs. And if you consider any complex having coordination number 5, and always you can think of 2 structural isomers, one is square pyramidal, one is trigonal bipyramidal, and if the energy difference between 2 geometries is not significant, then you can come across some sort of flexial behavior and switching from one geometry to another one. So, the molecular structure and infrared spectrum of iron pentacarbonyl are consistent with trigonal bipyramidal structure. So, it is not a square pyramidal, but when we look into 13C NMR spectrum, okay, it shows only one signal for carbonyl groups even at the lowest possible temperature. So, that means if you just look into iron pentacarbonyl is a trigonal bipyramidal complex. In this one we have 3 in the equatorial plane and 2 in the axial carbonyls. So, if strictly speaking when we look into 13C NMR, it should show 2 signals, one for equatorial and one for axial in a ratio of 3:2, but nevertheless even at low temperature 13C NMR shows only one signal. So, that indicates fractional process in which there is a rapid conversion of equatorial into axial and axial into equatorial. Though structural transformation takes place via a square pyramid structure and the mechanism is well known as Berry pseudo rotation. We also use another example such as PF5 to explain Berry pseudo rotation. I have depicted this in the next slide. You can see here how that happens. For example, you consider pentafluorophosphine and this is very similar to iron pentacarbonyl. For better understanding, I have given different colors for axial and equatorial ones. You see what happens due to the fractional process, these 2 axial will start moving towards the plane equatorial, and the same time these 2 in the plane will start moving towards the axial position by increasing this angle. That means simultaneously this angle, linear angle is decreasing and this 120 angle is increasing, and we reach an intermediate stage where these 2 are also decreasing from 180 and these are also increasing from 120. So, that we have a situation, it looks like a square pyramidal geometry. You can see these 4 are almost in the plane and this is in axial position, and then once the switching is completed, the equatorial ones have come to the axial position and those who are in the axial position have come to equatorial position. I had a very nice model to explain, probably in my next lecture I can show you the model for this one. It is very easy to understand. You can see clearly these 2 axial ones are moving towards the plane, that means this angle is shrinking from 180, and the same time these 2 have a 120 degree apart, they will be start moving and we reach this intermediate or transition stage where these 4 ligands, fluorides in this case, are in the plane giving a intermediate square pyramidal geometry, and once this rotation is completed you can see axial is turning into equatorial and equatorial is turning into. So, this is called Berry pseudo rotation. The 6 coordination complexes are very common among not only 3D but also with 4D and 5D elements. For a complex with 6 ligands, the most stable geometry is octahedral, and the majority of complexes with coordination number 6 assume this structure. But there are a number of chromium 3 plus and cobalt 3 plus complexes which are inert to ligand exchange reactions. For example, if you take hexamine chromium 3 plus and hexamine cobalt 3 plus, they are inert complexes, but usually when we make such homoleptic complexes with metal in lower reaction state, say chromium 2 plus is labile, cobalt 2 plus is labile, whereas chromium 3 plus or cobalt 3 plus complexes are quite inert for ligand exchange reactions. Octahedral homoleptic carbonyl compounds and also chloro compounds are quite well known. For example, chromium hexacarbonyl, molybdenum hexacarbonyl, tungsten hexacarbonyl, iron pentacarbonyl. So, these are all examples for homoleptic carbonyl, and here in all these carbonyl complexes metals are in their 0 valent state, and this is an example for rhodium in +3 state, hexachlororhodate you can say 3 minus, and also this is hexachloroplatinate 2 minus. So, platinum is in +4 state, and possible geometries for octahedral complexes when we have 2 different type of ligands in a ratio of 2:4 or 1:2 or 1:1 are these things. For example, you can have Ma4B2, in this case you can have geometrical isomers such as cis and trans. When you have Ma3B3, we can again have 2 isomers, one called meridional and other one is facial. And when we have coordination number 6, with the 3 bidentate ligands optical isomers are possible. The octahedral complexes show tetragonal, rhombic or trigonal distortions due to electronic or steric effects. That means octahedral complexes with even same type of ligands or homoleptic octahedral complexes need not be regular all the time. They can show some distortion, and this distortion can cause elongation of 2 axial, or it can be in the plane, and thus you can come across different type of distortions and having different type of point group, and of course we shall learn in more detail when we move on to crystal field theory at later stage. And tetragonal distortion in case of copper 2+ cases because of D9 electronic configuration is a typical example of John Teller effect. I shall elaborate more about John Teller effect in my future lectures in this series. You can see here octahedral complexes having Ma4B2 type showing cis and trans geometries. Similarly, when we have 2 bidentate ligands and 2 monodentate ligands, and if the relationship are can be cis or they can be trans, when they have cis, this can exhibit optical isomerism, whereas this one does not exhibit any optical isomerism because of planarity. And here when it exhibits optical isomer, the non-superimposable mirror image will be looking like this. So, that means Ma4B2 with B being monodentate ligand can exhibit optical isomerism as well as geometrical isomerism. Okay. So, when we have 3 bidentate ligands, so even if it is homoleptic, just for understanding I have given different color here, all are homoleptic. Even when they are homoleptic, you can think of having non-superimposable mirror image, and hence they can also exhibit optical isomerism. And when we have Ma3B3 composition, octahedral complexes having 2 sets of 3 ligands, they also exhibit geometrical isomerism. This is all these 3 ligands are in one plane. So, this is called facial, but in this case one set of ligands are in different phase, as a result they are called meridional complexes. That means we can come across, even in case of octahedral complexes we can come of cis and trans geometries and facial and meridional geometries, and also optical isomerism also we can see. A few 6 coordinated metal complexes also can adopt trigonal prismatic geometry because octahedral coordination is sterically less strained. Okay, for example, if you look into hexamethyl zirconium 2-, or if you just look into this rhenium complex, in both the cases here we have bidentate ligand is there, and here we have monodentate ligands are there, coordination number 6, and in this case and also in case of hexamethyl tungsten the geometries are trigonal prismatic. I shall tell you why these complexes adopt or have a preference for trigonal prismatic geometry over octahedral geometry. When I go to bonding concepts, I shall explain all these things in more detail. The bonding mode of sulfur atoms around a metal is trigonal prism in solid state. So, for example, if you consider solid state structures of MoS2 or WS2, the metal is in trigonal prismatic geometry. That means metal is surrounded by 6 sulfur atoms in a trigonal prismatic way in these cases. How about higher coordination? If we think of any coordination number higher than 6, it is not possible in case of 3D metals, but we can see in case of metals 4D and 5D because of their larger size, and there are several examples of 4D and 5D metal complexes exhibiting more than 7 coordination number, and hence geometries, corresponding geometries. For example, many tungsten 2 and molybdenum 2 complexes are known with mixed ligands such as carbonyls, halides and phosphines having coordination number 7, adopting either capped octahedral geometry or pentagonal bipyramidal geometry. And here I have shown one with coordination number 8 in case of molybdenum octacyano-molybdate. Here the geometry adopted by this one is square antiprismatic, and in this case ReH9 2-. There are 9 hydrogen atoms surrounding rhenium, tricapped trigonal prismatic geometry. So, let me stop this lecture here. So, let me continue discussing more about chemistry of transition elements in my next lecture.